After first video, we are continuing the electric heating in the second video. Now the topic is direct arc furnace. In direct arc furnace, there is the charge particle is placed into the secondary of a transformer of low, and secondary is LT side. Okay. In HT side, supply AC supply is given. After that, it is go to LT side. LT side means voltage is low, current is high. So in this case, in secondary, high current is required, and this current is allowed to pass through the charge particle. Okay, that's why the charge particle will be heated up. Indirect arc furnace, here also transformer action and arc is developed between between two terminals of the secondary. Here secondary is also LT side, but here direct uh, heating is not allowed. Here the charge particle is allowed to heat it up indirectly by the action of current passing through the secondary. That's why the charge particle will be heated up. And uniform heating can be achieved by the indirect arc furnace. And the safety provision is also high in the indirect arc furnace. Next one is induction heating. Here the figure shows core type induction furnace. Here single phase core of transformer action, you can see that this is the primary of the transformer core, and here AC supply is given. The secondary portion, there is no direct electrical contact with the primary, but there is the heating up due to transformer action. And here in 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 respect of where you are use this crucible, and this crucible contain the charge. Okay, and this charge particle will be heated up by the transformer action, but there is no heating up of the core, only the this portion, this charge particle or this secondary portion will be heated up, and uniform heating can be achieved with this core type induction furnace. But here the provision of risk, because after uniform heating of the charge particle, there may be possibility of the short circuit of the secondary. That's why we are going for the coreless induction furnace. Here in the coreless induction furnace, this is the secondary terminal, secondary wire. Okay, primary winding of secondary wire is given, and between this wire there is the transformer action, and the charge particle will be heated up because of current flowing of the this conductor. Okay, and uniform heating can be achieved by this coreless type induction furnace. Next one is high frequency eddy current heating. You know that eddy current loss is proportional to frequency square. That means that by changing the frequency, depth of the heating can be easily changed. That means that this is the particle which you are wishing to heat it up, and wounded up this wire, and this wire flowing the current. Okay, and this portion, this slab will be heated up by the eddy current action, and by changing the supply frequency of the supply voltage, you can easily penetrate the heating zone of this slab. Advantage of high frequency eddy current. First advantage is there is negligible waste of heat, because the heat is produced in the body to be heated. That means that the slab you are wish to heat it up is directly heated. Number two, it can place in vacuum or other special environment where other type of heating are not possible. Number three, it can be made to penetrate any depth of the body by selecting proper supply voltage. That means that by changing the supply voltage, you can change the penetration of the heating depth. Application of eddy current heating. Eddy current heating has been used for surface hardening, annealing and soldering of materials. Next one is dielectric heating. In the dielectric heating, dielectric material is placed in the secondary of the transformer. Okay, by which the current is split into two portions. One is for resistance, another one is for capacitance. Why capacitance? Because here in the secondary of the transformer there is two metallic part, and these two metallic part there is the dielectric medium. That's why there is the provision of the capacitive action. This is the IC, this is the IR, and this is the angle phi, and this is the angle del. It is mentioned that del plus phi is equal to 90 degree. Now power drawn is Vi cos phi. Current IC is equal to V by XC. XC is 1 by 2 pi FC. That means that IC is equal to 2 pi FC. P, putting the value of IC, that is the P is equal to V into 2 pi FCV cos phi. Now the value of phi is 90 degree minus del, because phi plus del is equal to 90 degree. Here the angle del is equal to very small, that means that cos 90 degree minus del is equal to sin del. If the delta angle is small, you can write is simply del. That's why P is equal to 2 pi FC V square into del. This is the power equation for dielectric loss, or this amount of loss has occurred during dielectric, and this power is directly converted to heat in this dielectric heating. Advantage of dielectric heating: since heat is generated within the dielectric medium itself, it results in uniform heating. Heating, because faster with increasing frequency, bad conductor can be heated up. Heating is faster method of heating. No frame has developed cleanliness, smooth control of the heating. Heating can be used directly. Dielectric loss is preferred, and application of this dielectric heating is plywood, for making the plywood, for breaking of sand, cast, plastic, for any kind of plastic, formation of the plastic. This type of heating is used. This is used for healthcare industry like biscuit and food industries, removal of moisture from oil. It is also used for removal of pain of human body. These are the various types of applications of dielectric heating. Now final last topic is infrared heating. In infrared heating, the temperature is utilized 2300 degrees centigrade, and here only 115 watt has been utilized to build this such amount of heating temperature, and it is widely used in the foundries for drying of metal. Thank you.